Hello students, I am Alejandro from Victory IB&C AIE Online Academy, and today we will be discussing the AP Physics 1, the 2019 paper, which will be divided into 5 different exercises. So make sure you watch all the video to have full understanding of each of the problems. Let's get started. So problem number 1, it's a 7-point problem with a suggested time of resolution of 13 minutes. It reads like this. Identical blocks 1 and 2 are placed on horizontal surface at points A and E respectively as shown. Okay, that's the diagram that we are given. The surface is frictionless except for the region between points C and D. So we have a bit of friction only in this region. Only there. Friction. Let's write an F and an R. Where the surface is rough. Beginning at time TA, block 1 is pushed with a constant horizontal force. Now this is a key word in here, will have a lot of implications in a few minutes. A constant horizontal force, it's not underlined for no reasons. Constant horizontal force from point A to point B by a mechanical plunger. Upon reaching point B, block 1 loses contact with the plunger and continues moving to the right along the horizontal surface towards block 2. Now, this is a crucial piece of information in here. Right here in point B is where the plunger releases the block. There is no more pushing force. Beyond point C, that means that between B and C, there are no forces, so there will be no acceleration. There are no forces other than the weight and the normal reaction force, of course. Those are the only two forces acting in this region that will cancel each other, so no acceleration at that point. Acceleration is 0. Where was I? Block 1 collides with and sticks to block 2 at point E. At point E, there's a collision in here. Whenever a collision takes place, conservation of momentum will be used. Collision. After which the two-block system continues moving across the surface, eventually passing through point F. Okay. Part A. On the axis below, sketch the speed of the center of mass. Of the center of mass of the two-block system as a function of time from TA until the block pass point F at time TF. The times at which block 1 reaches point A through F are indicated on the time axis. How's that? Well, we are kind of in a graph with no scale. On the vertical axis, there are no values, so all we can do is a sketch. That's what we are asked to build a sketch, to sketch the graph, sorry, and not to build a graph, since, well, there are no values, no numerical values given within this problem. And the horizontal axis is labeled with TA, TB, TC, TD, well, times at which the blocks are passing through each of the points that were labeled with those letters in the original diagram. So, what to do? Well, the first thing that we need to understand is how the speed of the center of mass of the system is related to the speed at which the first object is moving. Both objects start from rest, no object is moving, so we kind of know that our graph is going to start from this point, because there is no speed at time A. This will be the starting point, but the question relies on, well, how to sketch that graph. So here's what we need to understand. I will be writing some expressions that will be connected to the things I will be discussing with you. Of course, you're not expected to write what I'm about to write, but it will be helpful for me to communicate the ideas behind the relationship between the velocity of the first object and the velocity of the center of mass. So let's say that we label as xcm the position of the center of mass. How is the position of the center of mass calculated when we have two object system? These two masses are considered as punctual masses, so they just occupy one single point in space. They have the shape, the size of those two objects is not considered. So the position of the center of mass of the system labeled as xcm will be mass 1. Now this applies in any situation. Mass 1 multiplied the position of the first object plus the mass of the second object multiply the position of the second object divided the total mass. Let's say mass 1 plus mass 2. Now this is an expression that works in all times as long as you have two objects. Now in this particular case we were told that the blocks were identical. That means that both masses are equal. So instead of writing mass 1, mass 2, we can just write m. We can just write it. Of course, all the things that I'm writing on the right side of the screen might be extremely simple for many of you, and you might not really need to write them. But the formalism will be connected to these expressions. Okay, so same idea, just m multiplied position of the first object plus mass multiplied same masses, right? Position of the second object, and in the denominator we would have mass 1 plus mass 2, which will be just 2 times m, because masses are identical. Now within this expression, the masses can be simplified. We have mass as a common factor in the numerator and mass as a factor in the denominator, so the expression will become just 1/2 of x1 plus x2. Now this is a just in case thing. You can also write it this way, which might be obvious for many of you, but it's just in case thing. Okay, so you can choose any of these two final expressions. This is the position of the center of mass. Now this expression works in any situation in which both masses are equal. Now, if we take the derivative of this expression, considering time to be the variable, we will be able to derive an expression for the velocity of the center of mass. Now, the velocity of the center of mass will just be the time derivative of this expression, being 1/2, well, 1/2 is a constant, multiplied by the velocity of the first object plus the velocity of the second object, which in this particular problem, the second object is not moving, at least not until the collision takes place. So this is 0. There is no velocity of the second object, at least until the collision occurs, okay? So from, let's write it this way, from A to E, that means from the instant in which the problem starts until the instant in which the collision occurs, we can state that the velocity of the center of mass is just going to be 1/2 of the velocity of the first object. 1/2 of the velocity of the first object. That's it. So as long as we have a clear idea of what's going on with the first object, we just know that the velocity of the center of mass is just going to be 1/2 of it. And we're not really going to take use numerically of that 1/2, because values are not given. What we are asked to do is to sketch a graph. So let's sketch it. We are now in a position in which we can do it. So what happens between point A and point B? Well, let me zoom out just a little bit. That's it. Okay, between point A and point B, there was a constant force. A constant force will produce a constant acceleration. Now, that would not happen if instead of having a plunger, we were given a spring, right? Because springs, one of the things that they do is that they are able to push, but when springs push, they do it with variable forces, and variable forces will produce variable accelerations, which is not the case in here. Right here we were told, specified, that there is a constant force. So a constant force will produce a constant acceleration, and a constant acceleration will produce a linear increase in the speed. The speed of the first object from A to B increases linearly up to a certain value that we cannot know, and therefore the speed of the center of mass will also increase linearly up to half that value that we don't know. So we do not know the value, we do not know what half of the value is, but it's not really relevant. All we must do right here is to trace a linear graph that increases up to a certain point, up to any point. Any point will be okay. You can go just up to here, wherever you want to reach, it's fine. As long as it's a linear graph that increases at a constant rate, you are okay. Now, between point B and C, that means between TB and TC, those times we discussed before that there was no acceleration, meaning the speed is constant, so the graph continues linearly but horizontally, this way. Once point C is reached, the friction zone is entered, and within that region there will be a force, a friction force, that will produce a deceleration. And friction forces are considered to be constant, so same idea, right? Constant friction force decelerating the object, so the speed will decrease linearly. So up to any value that you like, I'll try to go up to this point. This is what you're, something like this. Whoa. That's it. So constant increase, constant region, constant speed, and then decreases. From D to E, well, there is no acceleration, there is no forces, so the situation from D to E, it's, in terms of acceleration, it's the same as it was from B to C. There is no acceleration in here, so whatever the velocity or the speed was at D, it will remain constant. So another horizontal region right here, and this is where the collision takes place. Okay, this is where the collision occurs. So we need to have a short discussion of what happens during that collision. Okay, so whenever two objects collide, we do know that there is a magnitude called momentum, linear momentum, that it's conserved. So during the collision, let me just write it here, at point E, where the collision takes place, we do know that the momentum of the system is conserved. The momentum of the system. How can we know that? Well, there is a principle called the law of conservation of momentum that states that within a system, if there are no external forces acting, the momentum of the system will be conserved. And during that collision, the only forces that are acting between the objects are internal forces. Object 1 pushes the object A, producing an increase in the speed of which object 2 will be moving, because it was at rest, and after the collision it will be moving. And the speed of the first object will be decreased after the collision. What I just said is not entirely true, because I just said that the conservation of momentum requires that there are no forces acting. And there are forces acting, but within this problem, those two forces are cancelled. We have a weight acting downwards and a normal reaction force, so that there is no net external forces acting on the system. There are two forces, weight and normal for the first object, weight and normal for the second object. Those two forces are cancelled. There's nothing going on vertically, so the conservation of momentum applies both horizontally and vertically. Now, what I just wrote in here is that the initial momentum is the same as the final momentum. Initial momentum being, in any situation involving two objects, we'll say something like mass of the first object by the velocity of the first object, plus mass of the second object by the velocity of the second object, equals Now, for any plastic collision, there is only one final velocity. There is only one final velocity. Both objects will stick together. That's what we are told. And this can be the total momentum of the system. The final situation, it's just going to be the sum of both masses, right? This multiplied by the final velocity, whatever that final velocity is. Now, in this problem, we know that before the collision, there is no speed of the second object. So this is zero. This is zero. And we also know that the masses are identical masses. So instead of writing mass 1 and mass 2, I can just write mass. So mass times the velocity of the first object right before the collision, that would be the velocity right before reaching point E, equals 2 times mass, whatever that mass is, multiplied by the velocity of both objects, the velocity of the system, of the sticked system, mass 1, mass 2. And this expression, mass, can be simplified, and we can state that the final velocity of the system, we can state that, let me zoom in just a little bit. The final velocity of the system is equal to the velocity of the first object right before the collision. Well, there's a 2 missing. I can choose to write this 2 multiplying on the right side, or write 1/2. I'll write it as 1/2 on this side. Now, this is a crucial piece of information. The fact that the velocity of the system, it's 1/2 of that velocity that object 1 had before the collision. And in the graph that we were sketching, at this point, what is being represented in the vertical axis is the speed of the center of mass, which already is 1/2 of the speed of the first object. That implies that the speed of the center of mass of the system is not changed during the collision, will remain being the same. So there is no effect, no visible effect in this graph. Bear in mind that this is a graph for the center of mass, and the speed of the center of mass is not affected by a collision. The speed of the center of mass is not affected by a collision that might affect the velocity of the first object, might affect the velocity of the second object, but not the velocity of the center of mass. So that's the end. You must reach this point. This is what you are expected to do. You're not expected to write the word collision here. So your graph should not include this. You're not expected to include this. That's it. So thanks for watching. Please do watch my next video for the remaining part of the problem, as well as the remaining part of the exam. Also, don't forget to register on our website www.victoryonlineacademy.com for free demo registration. I'll see you in the next video.